My name is Amrita Bhatnagar. I am from CSE Department of AKGE. Today I am going to explain a very important topic of operating system, Peterson Solution of for critical section. Okay, so for understanding the solution of Peterson solution, we have to understand what is the critical section. These are the main outline of this lecture: process synchronization, critical section, race condition, necessary condition for critical section, synchronization mechanism, solutions for critical section problem, Peterson solution, and then their advantages and disadvantages of Peterson solution. Fine. To understand the Peterson solution, firstly we have to understand what is the process synchronization and critical section. Firstly, we will understand what is process synchronization. What is process synchronization means? It is a coordination of execution of multiple processes in multi-process system to ensure that they access shared resources in controlled and predictable manner. For example, if we have more than one processes which are executing simultaneously, then and they are using shared resources like some shared variable and other shared files also, then it should be executed in controlled and predictable manner so that their data can be in the consistent state. It should not be in the inconsistent state. The main objective of process synchronization is to ensure multiple process access shared resources without interfacing with each other and to prevent the possibility of inconsistent data due to concurrent access. To achieve this, various synchronization techniques are there. For example, semaphore, monitors, and critical section. So, for the process synchronization, we need different type of synchronization technique. So, we have understand now what is the meaning of synchronization where we have multiple processes running simultaneously and we required a process so that they can be run in a controlled and predictive manner. Fine. This is the process synchronization. Now, for the process synchronization, we have actually two different type of processes. First one is independent process. Independent processes are those processes which don't share any data. So there are no data sharing. So there is no problem in the execution of the independent process simultaneously. And another category is cooperative processes, a process that can affect or be affected by other processes executing in the system, because this cooperative process takes sharing data, sharing variables also. So it can be there can be different values of the sharing data. So it should be executed in a controlled manner. For example, producer-consumer problem, where producer produce a different products and consumer consumes the products. But there should be synchronization mechanism between the producer and consumer. If producer produce more products but consumer cannot consume that much products, then there will be problem. So there should be a process synchronization techniques apply in this problem. Process synchronization problem arises in the case of cooperative process also because resources are shared in the cooperative process. So it means we don't have any problem in the independent processes because in this case we don't have any sharing data. But in the case of cooperative process, we have some difficulties regarding the synchronization because in this case we have same common variables, and when these different multiple processes changes the value of common variable, then there can be inconsistent data in the system. So we have to avoid this type of problems, right? So process synchronization problem can be arise in the cooperative processes. Now, we should understand what do you mean by the critical section. Why we have critical section? Critical section is a code segment or that a important part of a particular process where we have shared variables which need to be synchronized to maintain the consistency of data variables. So you can see in the diagram we have, this is the critical section portion of a particular process. This is a section where we have common variables. These common variables will be executed by multiple processes. So each and every program or process will have its critical section, but there should be some rules and regulation to enter in the critical section. Fine. If every process will execute critical section without any controlling mechanism, then there will be inconsistency in the data. Fine. Now you can see here there is a entry section and exit section also. What is the need of this entry and exit section here? Because multiple processes cannot enter critical section in a simultaneously or in a one time. There should be some entry condition to enter in the critical section to a process. Firstly, we have to, it will check the entry condition. If the condition is satisfied, entry condition is the satisfied, then process can enter into the its critical section. If this condition is not satisfied, then process cannot enter in its critical section. And when critical section is executed, the work is done, then there should be a exit section. And again, exit section will be executed. And after that, after the critical section, there is another section which is known as a remainder section. The remaining section is known as a remainder section. And okay, after the executing the critical section, process will execute remainder section. So in this case, we should understand that there can be multiple processes, and each process will have its critical section portion where we have sharing variables, but sharing variable cannot be changed simultaneously or without any permission. It cannot be changed. That's why we have critical section portion in each and every process. But in the critical section portion, only that process can enter which satisfy the entry condition of the process. If entry condition is satisfied, then only process can enter into the critical section. Otherwise, it cannot. It have to wait to enter the critical section. If the other process is using its own critical section, then it have to wait. Then this condition will not satisfy. Fine. And after the completion of the critical section portion, it will execute exit section, and turn will be provided to the other processes, and then it will execute remainder section. So this is the concept of critical section. Now, what is race condition? Okay, race condition generate when we execute multiple processes, and multiple processes are operative processes are there, and these processes have sharing data, sharing variables. Then there can be inconsistency in the data. It means a particular variable can have more than one values, which is known as an inconsistency in the data. So to remove this type of race condition, we have to apply some synchronization mechanism. We have to apply some solution for this type of race condition. Firstly, we have to understand what is the meaning of this race condition. When more than one process is executing the same code or accessing the same memory or any shared variable in that condition, there is a possibility that the output of or the value of the shared variable is wrong. So for that, all processes doing the race to say that my output is correct. This condition is known as a race condition. It means if there is a variable which is shared by the different processes, in the different processes, after the execution of the different processes, the variable value can be differ, and every process said that this is the right value. Then this is like a race, and this is known as a race condition. A race condition is a situation that may occur inside the critical section. Fine, it will always occur in the critical section, because critical section is that section where we have common variables or shared variables. Fine, this happens when result of multiple thread execution in the critical section differs according to the order in which the threads execute. Race condition is critical section. In critical section can be avoided if the critical section treated as a atomic instruction. So that it means we have to avoid race conditions in the critical section. Race conditions are in the critical section, and critical section are that section which have common variables of the different processes, and we have to avoid the race condition because there is the data redundancy or data inconsistency is not required in the in our system. That's why race condition should be avoided. Fine. Now, we should understand race condition. What are race condition? How it is generated. For example, we have two processes P1 and P2 are executing concurrently. Fine. Both the processes share a common variable name count and the initial value of count is 5. Fine. Process P1 tries to increment the value of the count. One process name is P1 and it wants to increment the value of the count. But process P2 tries to decrement the value of count. Okay. Now the value will be different. Fine. When the process P1 will execute, the count value will increase, and when the process P2 will execute, then the count value will be decreased. Now you can see here, this is the example. P1, you can see here, P1 and P2, two different processes. And now you can see here, this is a common variable count. Fine. Okay. Now this particular process P1 is incrementing the count variable, and this particular process P2 decrement this count variable. And this count variable, because in this section it has a shared variable, that's why it is known as a critical section. This is known as a critical section portion of these processes. Fine. Because we have here shared variable, but this process wants to increment the value of count and this process wants to decrement the value of count. So this is the two different processes. Because now what will happen if we check the scenario? You can see here. Now you can see here, this is the assembly language for this operation for incrementing the count variable and for decrementing the count variable. We have three statements here. One, move the value of count into the R0 register. Second, increment the value of R0. And third one is, again, transfer the R0 data into count. Then what will be the value of count? If the starting value of count is 5, then in this case, when the P1 will execute here, then we will increment the value of count. Then the value of count will be 6 here. Fine. Now in this case, we can see here, there are three statements here, 1, 2 and 3. Firstly, move count to R1. The value of count, which is 5 in this time, can transfer from count to R1. Now decrement R1, the value of count will be decreased here, and move again the value of R1 to count. Now the value of count will be 4. So that these two processes, one process is going to increase the value of the count and second process will decrease the value of count. But if these two processes executed concurrently, then what will happen? Then it can give different results here. The value of count can be different. We can see here in the different sequences of the execution. First case we will see here when the process P1 will execute first and then process P2 will execute. P2 will be execute next time. For example, firstly P1 will execute, then we will get here 6. Value of count will be 6. Again, when after the P1, when P2 will execute here, it will decrease the value of count because this time the value of count is 6. Fine. Now the next, after decreasing the value of count will be again 5. In the case of case 1, where we will execute all the P1 process completely and then we will start P2 process, then it is okay. The count value will be 5. Fine. Or there is another case where we will start with the P2 process, we will decrement the value of the P2, then we will increase the value of the count with the help of P1. Then again the value will be 5 because it will decrease when the value of count is 5, then it will decrease the value of count 4. And now value of the count is 4. Now When P1 will execute, the value will again become 5. Okay, so when the process is executing sequentially, firstly P1 execute, then P2 execute, then it is okay. The value will be, count will be 5. But if there is a context switching, then there will be some problems. You can see here. You can see here in the case one which I have discussed, firstly P1 process will execute completely, then P2 process will execute completely. Then the count value will be 5. Okay. And there is another case, because in this case both processes are running sequentially, fine. And another case, when P2 process is executing firstly, then secondly P1 process will execute, and the final value will be 5 here. So we can see that the value of count will not change if the processes are executing sequentially, but it is not practically possible. There is a concept of context switching in our system, where some instruction will execute it by the CPU and then context switch to the another process. So then there is a possibility of other sequence of the execution. So we are taking the another case of context switching, when the context switching is possible. So we can see this is the case 3. In this case, you can see here only P1 first instruction is executed of the P1, then P2 context switching will be done here, and P2 the first instruction will be executed, second and third instruction will be executed of P2. Then again control comes to the back to the P1, and again now instruction of the 2 and 3 of P1 will be executed now. But the answer of this time will be, the count will be 6. But in the case of previous examples, we have value of count is 5, but in this sequence we have value of 6. This is known as an inconsistency in data. So this, and again this is known as a race condition in the system. So it should be avoided. It should not be possible. It should not leave the data in an inconsistent form. So race condition can be arise in the critical section only. Why it is in the critical section? Because we are having here, you can see here, this is the critical section where we have a common variable. Okay, so when the common variable will change simultaneously, then this race condition will arise, and it will leave the data into inconsistent race, which is totally not required in the system, which is undesirable state. Fine. So we have to avoid race condition. We have to solve this critical section problem with a different type of synchronization mechanism. Now we will see here some necessary condition for the critical section problem. Now if there any solution will be there for the critical section, it should be satisfy these 3 necessary conditions. First one is mutual exclusion. Mutual exclusion means only one process can execute its critical section at one time. No other process is allowed to execute critical section at that time. That means it's known as a mutual exclusion. Only one process can enter in its critical section at that time. If there is one process in the critical section, then other process we have it have to wait for its previous process. Fine, it have to wait. It should wait. Now next is the progress. What is the meaning of progress? Progress means if no process is executing in the critical section and other processes are waiting outside the critical section, then only those processes that are not executing in their remainder section can participate in deciding which will enter in the critical section next, and the selection cannot be postponed indefinitely. Fine. What it means? It means if there is no process executing in the critical section and many processes are waiting outside the critical section, then there should be decided then which process will enter in the critical section. Then only those processes will participate in the deciding which will enter in the critical that are executing, that are not executing its remainder section. Fine. This is known as the progress. The another meaning of the progress is that no other process will stop to a process to enter in the critical section. If any process don't want to come into the critical section, then it will not stop to another processes to come into the critical section. Now, next is the bound waiting. Bounded waiting means number of time a process number of time enters in the critical section. This should not be there should not be a condition of starvation. Only for example, if we have two process P1 and P2, and P1 is number of time P1 enter in its critical section, but P2 is in the state of starvation. So this is an unnecessary condition. It should not be bounded waiting here. So what it means, a bound must exist on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. Fine. This is known as a bounded waiting. So there should not be starvation state, because each and every process should get its chance to come into the critical section. So again, I am repeating these three conditions for the necessary condition for the critical section. First one is the mutual exclusion, where only one process can enter the critical section. Fine. No other process can enter the critical section if there is a one process in the critical section. Another process you have to wait outside the critical section. Progress means no process that process will stop the other processes who are not interested in the critical section. They will not block or stop the particular process to enter in the critical section. Fine. Bounded waiting means number of times a particular process can enter in the critical section, and there should not be a starvation condition in this case. Always we have to check how many times we have to allow a particular process to come into the critical section. That is known as a bounded waiting condition. So these are the necessary conditions which a particular solution have to satisfy. To solve the critical section problem. These are the three necessary conditions here. Now we have synchronization mechanisms to solve the critical section problem. First is with busy waiting, and another one is the without busy waiting. Now, what is the meaning of busy waiting? Busy waiting means, for example, if this is the critical section, and in this critical section, if there is a process P1, and now P2 again, and there is another process P2 which also wants to come into the critical section. So, when P1 is in the critical section and P2 will wait outside the critical section continuously. When P1 will complete its work and come to outside the critical section, then P2 will come into the critical section. But that till that time, P2 will wait for the critical section continuously. This is known as a busy waiting. So this is a drawback of a particular mechanism. This is this will decrease the CPU utilization. Busy waiting will decrease the CPU utilization, because CPU is unnecessary waiting for a particular task. It is not doing some useful task. So busy waiting is not required. But many of the synchronization mechanism is using busy waiting. Fine. And another is the without busy waiting. In this case, what will happen if the critical section is occupied by the P1, then P2 will not wait outside the critical section. It will go into the sleep mode. When it will go into the sleep mode, then CPU will not waste its time for waiting, and it will be busy into the another important task also. Fine. So, after when the P1 will complete its work and it will come outside the critical section, then P2 will again will be active and again go to the critical section after the P1. This is there can be two types of mechanism. Many mechanisms will follow the busy waiting concept, and some mechanism follow the busy waiting, without busy waiting mechanism. Right? Now, these are the solutions to the critical section problem. Lock variable, test and set, Decker's algorithm, Peterson. These all are the solution for the critical section. We can use this all solution for the, but the best solution is Peterson algorithm. Why it is best solution? Because it can preserve all the necessary conditions for the critical section, which I have already explained here. You can see here, these are the three necessary conditions for the critical section. These critical section problems condition can be preserved by or satisfied by the Peterson solution. Now we will see what is the Peterson solution. Peterson solution is one of the most widely used solutions to the critical section. It is a classical software-based solution. This is a software-based solution. We have to notice there. In this solution, we use two shared variables. First one is int turn, for a person whose turn is to enter the critical section. So, we have a one particular variable turn here. What it means? Turn means which process will have this time turn for the using the critical section or enter in the critical section. And there is another variable or flag, Boolean flag, which have value true and false. The value true indicates that the process wants to enter the critical section. It is initialized to false. It means indicating no process wants to enter the critical section. Fine. So, when the value of flag is true, for example, we have process 1, then flag of process 1 is equal to true. What it means? It means particular process or P1 process wants to enter to the critical section. Fine. If the value of turn equals to 1, it means this time we have given the turn to the process 1. Fine. So, these are the two main variables in the Peterson solution. We have two variables. Now, how it will work? You can see here. This is the code for the Peterson solution. So, you can see here, if the flag I is true, for example, this is for the I process, then turn will be given to the another process. This is the main thing. If firstly, in the case of Peterson solution, firstly flag of particular process P1 will be true, then turn will be given to the another process J, and then we will check the condition if the flag J is true and turn is also J. We have given the turn to the J, and if J process also wants to come to the critical section, if both conditions are true, then J can enter the critical section and it will not, then I process will not do anything. It will here busy waiting. Fine. Because already J process wants to come to the critical section and turn is also given to the J process. And when this critical section will be executed by the process J, after that, what happened? Then after the J, I will come to the, when this condition will false, I will come to the critical section. It will execute after J is critical section, and then after that, this is the exit section where flag I will be false, because now it already executed its critical section, then it will change its flag value false, because now it don't want to execute its critical section, and then again it will come to the remainder section, then it will execute remainder section. It's fine. So, this is the Peterson solution. Now, we will see with the help of another example. You can see here we have process 0 and process 1. Fine. Here you can see here for the process 0, if process 0 flag process 0 is true, it means, what it means, process 0 wants to come enter to the critical section. Fine. Turn 1, but it will give to the turn to process 1. If the flag 1 and turn 1 both are true, then it will process 0 will not do nothing. Fine. And it will give the turn to the process 1. And when this condition will false, when one of these conditions will false, then only process 0 will come to the critical section, and after the executing this critical section, it will false the flag 0. Flag 0 will false after that, because now it already have executed its critical section, and then it execute its remainder section. In this way, process 1 will do all the work. Flag 1 is equal to 0, true. It means process 1 wants to enter the critical section, but turn to given to the 0 process. And then check the condition. If process 0 is also enter through the critical section and turn is also given to the process 0, then if process 1 will do nothing. Critical section will be executed by the process 0. When it will complete its execution of the critical section process 0, then this condition will be false, because it will change its flag value, then its condition will be false. Then only process 1 will come to its critical section, and it will execute its critical section. After the execution is of its critical section, the flag value will be false. This is the exit section, because now it don't want to enter into the critical section. That's why the value of the flag 1 will be false, and this again, this will execute its remainder section. So this is a solution of Peterson solution. So it is very good solution, because it will preserve all the necessary condition of the critical section. First is the mutual exclusion, because in this case only one process can enter into the critical section. Both processes cannot enter in the critical section. Second one, the progress. So no process will block the other process. It is going to give turn to the other process. You can see here these processes are given the turn to the another process, and another one is the bounded waiting. So there is no condition of the bounded waiting, because turn will firstly we will one process will get the turn, and another, then it will give to the turn to the another process. So there will not be bounded waiting also. So that these three conditions of the critical section will be preserved here. So that's why it is a very good solution. Peterson solution. Now we will see what are the advantages of disadvantage of Peterson solution. Advantages are these are the advantages: mutual exclusion, progress, and bounded waiting. All three properties are preserved by the Peterson solution. Fine. This is the main advantage of Peterson solution. And now the disadvantage. What are disadvantage? Disadvantage of Peterson solution is limited for the two processes only. We don't have more than one processes here. This is the algorithm or solution for two processes only, but it involves busy waiting, which is a disadvantage of this mechanism. Okay. Okay, thank you. I think you will understand easily Peterson solution in this lecture. Thank you.